My pictures can't compare, but I'll make a copy of this we'll take a little break in the middle. What I did was write up the whole thing about the quadrature of the circle in a somewhat more leisurely way than the book. And I figured out what was wrong with the book. There's a couple of things. I drew my own pictures here, which will show you. So you're given a parabolic segment there. And Archimedes' great result was to find the area of it. Oh, you need light, don't you? You need light for that? No. Okay. That was it. Okay. You're given a parabolic segment, and you'd like to construct a tangent to the parabolic segment. This little aspect was not adequately discussed, I think, in our text. This is the Archimedes quadrature of the parabola. So you draw the tangent. The Greeks knew how to draw tangents to curves, so they could do that. Now I've labeled that AB. Now that determines the point C, the point of tangency. So you construct that triangle. And that's the triangle, 4/3 of which is or 4/3 of its area is the area of the parabola segment. So that's the sum and substance of Archimedes' theorem. It's not clear in our book how the point C is determined, but that's how it's determined. You can construct a tangent parallel to a given line synthetically. You do that, now that defines the triangle ABC, which then leads to the theorem. So after you have ABC, you construct the bisector for the point that lies at the center, in the middle of AB. That's point P. I'm going to give you this anyway. And it's on, apparently we're on TV too, so it's a multimedia presentation. PC is the line you get by connecting the point of tangency to the bisector of AB. In our book, it gives you, and I couldn't understand this, it said draw a line, a vertical line, parallel to the y-axis, and this will automatically bisect AB, and I didn't see why that was true. One of the problems with that figure 13 in the book was it's grossly out of scale. They just did a bad job of picture editing. Anyway, okay, so you have that. The next thing you do is rotate the whole mess so that this line CP is vertical, and you impose a coordinate system now. The y-axis obviously is parallel to it, and the x-axis is tangent again to the parabolic arc. So this point of tangency and this point of tangency have nothing to do with one another. They were tangent for different purposes. This point of tangency is the tangent that's parallel to the base of the segment. This point of tangency is just the one that you get by bringing a line up from below so that this line is parallel to the y-axis. So I make this the origin of the system of coordinates. And the proof in the book, I'd like to find a purely synthetic proof, which Archimedes evidently had. The proof in the book uses a little bit of analytic geometry, which, of course, as you know, or may or may not know, wasn't available formally until about 1637. Basically, an invention of Descartes. I think he wrote a book called La Géométrie, which in 1637, which introduced the techniques of analytic geometry. Not only that, but the proof that's presented in our book uses a little bit of calculus. It calculates a derivative. I have a feeling that Archimedes may have had a synthetic theorem that says something to this effect. You know how they used to state those things? If a line be extended, they sound like pirates, If a line be extended, right? If a line be extended parallel, I guess I can lose the accent. If you have a line here and it's tangent to the parabola and you extend it a certain quantity, then the vertical, or words to this effect in ancient Greek, the vertical change would be thus and such. In modern terms, you say that the parabola has an equation of the form y equals ax squared, and then you evaluate 2ax, which would be the derivative, at the x coordinate of the point of tangency to get the slope there, right? That would be the slope. And then if you go out this much, you go the slope times that gives you this much, right? So that argument's used later on in the calculation, but it's kind of hidden when you first go through it.
There was no history behind
This is the book that Chuck used.
Yeah.
Is the entire thing?
Proof of something.
Yeah.
I don't know if there's a lot of sections.
So he did it with a lot of proportions, center of gravity, loss, and levers, and there's a couple fudges in here.
Yeah, there was.
I'll have to get this book and try to rationalize the history of math.
Yeah.
You must have probably absorbed mine.
You know what? This is the one that I can't draw.
That doesn't do it.
That's don't worry.
Anyway, so you have the coordinate system overlaid, and let's see, what do we do now? Oh, we connect the ends of the parabolic segment. We already did that, didn't we? Yeah, okay. We did all that. Figure 6. All right. What's new? Well, here's what's new. We construct the parallelogram that's implied here, right? So we actually do that. Generate that parallelogram. Call this little point here Q, and then construct the vertical, necessarily vertical, bisector of the parallelogram, which is FH. Okay? So this dotted line here, all the construction lines are dotted lines. The lines of the figure and the triangles are solids. And the parabola itself is a polyline. It's a little bit heavier than the others, so you can see that built up. It's much clearer. That's not too bad here, is it?
Yeah. I think it's probably.
Yeah, it is a little wavy, but I'll give you the hard copy. So I construct this bisector, HF. So this little parallelogram and this little parallelogram are congruent, make up the big one. Okay, that's important to have that line there, because we need to use those two parallelograms to get relations among the triangles that are appearing now. Okay, now we construct triangle CEE. We do that by wherever this bisector of the original big parallelogram was, where it hits the parabola, we label point E and go from C to E and E to B. So that makes triangle CEE. Okay? All right.